Hey class, it's Travis Bledsoe again. We'll do a second video. It'll be our first section video over the presentation of hand tools. You should have the PowerPoint available to you, D2L. First, I need to go over the roll book to make sure I've got everybody listed that's supposed to be in the class, and make sure I have your name listed as you want to be called. So we've got Seth Bland, Isaac Bourne, Austin Klaus, Mia D'Amico, Ben Denton, Christian Farmer, Cody Hancock, Kevin Haynes, William Powell, Samuel Wilkins. So if I didn't call your name, please let me know. I don't have you listed in as registered for my class, so need to make sure we get that straightened out sooner than later. And also, I need you to let me know if you've got a preferred name. Some people go by middle names or go by abbreviated name. So just let me know what your preferred name is if you have one. So I'm going to go over the hand tools section. This is the longest presentation that we've got. I've pared this down quite a bit from where it initially started. And then our next section for the power tools is our second longest. So we're getting the hardest ones out of the way up front. And bear with me as I go through the video. I'm not much of a video maker, and I don't like to have my video recorded or audio, so this is a struggle for me to do this, but I think there's going to be some value in it, I hope, to where you can replay the videos. You can watch them at your own time, and then ask questions later, during our Zoom meetings, or email me questions that you've got through. You can email them at the D2L or northeaststate.edu email, or you can call me. I list my cell phone number there, so on the D2L site. So I'll go through this presentation and hopefully make some sense out of it for you. Basically, it starts out as a basic hand tools presentation. So as I go through it, try to give some much detail and clarity about each device that we talk about, and we can do hands-on. We come together in the labs. So I'm going to turn my mugshot off, where you don't have to look at my ugly bald face, and then we can just go through the presentation now. Okay, here's the categories we're going to be looking at: the measuring tools, fastening tools, cutting tools, driving tools, and things that's listed in the other category. So measuring tools, we're not going to get into way in depth into measuring tools in this hand tool section. We've got a whole section devoted to precision measuring, where we're going to cover all these things again. This will be a kind of introduction to what they are. So tape measures, you've probably seen tape measures. They're coming different lengths. They're used more for carpentry type work. They're not precision measuring tools. They typically are graduated down into the 1/16 of an inch, but I have seen them down into the 32nd, but they become hard to read at that point, and they're not very precise because the tip on the little silver hook tip on the end of a tape measure, it moves back and forth, and it's supposed to do that, and the reason why is that it moves so you can do inside and outside measurements. So it typically moves the thickness of that metal clip on the end. So that's the thickness that it should move. And so when you butt it up against something, it should move in. And then when you hook it on something and pull out, then it'll go out to do an outside measurement. So rulers, that's shown down in the bottom. These come in different lengths. That particular one's a 6-inch rule, often referred to as a machinist rule. That one will have 4 graduations on it. You're seeing one side of it there, and it looks like it's maybe the 32nd and the 64th shown. I can't hardly see it very well. But those rules, typically we flip it over, it'll have 2 other graduations on it. So they're going to have graduations in the 8th, the 16th, 32nd, and the 64th. You get down into 64 little lines within a 1-inch mark there. That becomes pretty hard to see with your eyes. At least my old eyes, that is. Um, if you need to measure even more precise than a 64th, we get into micrometers and calipers. Micrometer is a horseshoe-shaped looking device there, and it measures in 1 inch increments. So if you get a bigger, if you need to measure, say that one's 0 to 1, if you need to measure from 1 to 2, you need to get a different micrometer. You've got protractor listed off to the right there. That's to measure and detect angles. We have thickness gauges, which are not listed on this slide, but all it is like little thin pieces of metal, and it's actually a tool that's made and manufactured. Thicknesses usually range from about a thousandths, maybe a half a thousandth. I don't know if it'd be down that low. Thousandths up to maybe 40 thousandths of an inch, and in half-inch increments. So we've got combination square. That's a tool we'll use quite a bit in our labs. Hopefully we can get together in our labs and make good labs. We'll have struggles with the social distancing and things in our labs, but hopefully we can make it work. So these combination squares, they have a rule. There's the picture there at the top. That's your common square head. It's got 90-degree angle when it's on the ruler and a 45-degree angle. You can loosen that, looks like a brass knob there in the middle. Loosen that up and slide it along the rule back and forth and tighten it back down. That one that's shown there. It's hard to see, but toward the top edge there is a spirit level. It's also can be used as a level. So you can hold the rule part up against the wall, and it'll show whether the wall is plumb, or you can sit the bottom edge of that square head down on the table and see if it's level. Sticking out the end of that, it looks like a little button there at the top of it. That's actually a scribe. It goes into the end of the combination square. Scribe is just a sharp metal point, and typically they're about an inch and a half long. And that's why you don't have to use a pen to write on things. You can use the scribe to scratch into it. Like a piece of metal, you can scratch into it and cut along that line or make a punch mark, whatever you're trying to do with it. Down the picture in the bottom right, you'll see two different heads. You got three heads on that. We talked about the square head. That's the 90-degree and 45-degree. The one in the middle is a protractor head. You loosen that up and it spins around, and you can check up to 360 degrees of angle. So you can make markings or verify marking or angles with that. That other device that's on the left side of the rule in that bottom picture, that is called a center head. So you see how it's actually in a 90-degree angle if you look at it in the right direction. It's got a 45-degree to the rule. So if you take a round object, say you take a 3-inch round piece of aluminum stock or something like that, and you can sit that round object down into the cradle of that center head, and you've got the ruler going right across one edge. So if you take your scribe and mark along the ruler onto that aluminum piece, you make a line on that, then rotate your round stock, rotate it 90 degrees, and then make another scribe and look at it, and you'll have an X there. And where the two lines cross, that will be the center point of that round object. So you can make a drill mark there or whatever you need to do. So that's a good tool to use to find the center mark on the round objects. So I'm just kind of going off cuff here, looking at the red text. That is what things you'll need to know for the test, as I mentioned on our introductory August 17th. So combination square, test the work for squareness, check 90-degree, 45-degree angles, check the level or plumb of surfaces. You can check and measure lengths and widths using the ruler. And also the ruler can be used as a straight edge or use the square head and the ruler together to mark. You can slide it down to make a marking tool. All right, precision measuring tools. Okay, dial calipers there in the top left. There's I'm teaching on dial calipers because they're a little bit older technology, but you need to know how a caliper works. I actually have digital calipers out today that are really simple to use, but people tend to look at them and they don't really understand where the reading comes from. So if we learn how to read the dial caliper, then you can understand the measurements, and when you use a digital, you'll just appreciate the digital factor much better. I appreciate the dials because when I first started learning to use precision measuring tools, we had vernier calipers, and those were really tough to try to figure out how to read those. So dial calipers reads down into thousandths of an inch, and pretty neat tool. They're range, 6, 8, 12 inches long on the scale. So, and they measure outside down the bottom of um, the teeth are open there, the forks. You can see the jaws opened up. Um, that is down the bottom part. You measure the outside measurements. On the top, you'll see two little jaws sticking up. Those actually will go inside of something. So if you'll measure the diameter of a hole, use those parts to measure inside diameter. Then look to the right side of that, and you've got a little thing, a little piece sticking out from the end, and that is measured depth. So as you roll the center part, you get the thumb wheel there, you roll that, it opens it up, opens up the jaws on the bottom, on the top, and then it pushes the depth gauge out the end of it. So we'll get into more detail on reading those in the precision measuring section. So the micrometers, we've got uh, on the top one, we've got three shown. The top one is outside micrometer. It's a horseshoe shaped. That is a fixed micrometer. It measures, that particular one is 0 to 1 inch. And they're all in 1 inch increments. So if you need to measure from 1 to 2 inch or 3 to 4 inch, you'd have to get one that measures that. So to have a full set, it could be quite expensive if you need to measure a lot of different lengths of devices. So the dial calipers, is a tool that it's probably just about as expensive to buy one dial caliper as the micrometer, but dial caliper can measure a much wider range than the um, outside micrometers. Now the inside micrometers, and that is the one that's in the middle. Now that has one micrometer head that has interchangeable rods that go in it. So if you buy one set, you get a bunch of different rods, and it's not quite as expensive and as big a set. And the same for the depth micrometer, which is the one on the bottom. It has interchangeable rods in it as well. So you've got one micrometer head. Now all three of these, you read them exactly the same way. So when we learn to read those, you're going to, if you know how to read one, you can read all three. So we're going to learn basically using the outside micrometer. That's the most common. However, on the depth micrometer shown on the bottom, the scale is backwards. What I mean by that is the outside and the inside micrometers, the top and middle. Your 0 is on the left, and it goes 0 up to 9. On the depth micrometer, your 0 is on the right side, and it goes 0 to 9 on the scale from right to left. But you read it just the same. Okay, your thickness gauges down the bottom right. I briefly talked about those, so that's what those look like. You can get those in longer versions. I have some at home, a couple different sets in about 10, 12 inch lengths. So get back into hard to reach places. I've got some that's made out of brass, some made out of stainless. Telescoping gauges, top right. Those are pretty neat devices. Don't see those very often, but we've got some in the lab, and I'll show you and give you hands-on with those. Quickly, the explanation of those. You see look at the middle one there, the biggest one. You get a little plunger sticking out both ends. There's a plunger on both sides. You push that in, it's spring-loaded, and it'll pop back out. If you push those in together and then tighten that little knob that's shown on the bottom, it holds your little plungers inside. So if you want to check the bore of a cylinder, so you take an engine apart and you want to check down in the middle, check the diameter of that bore in the middle of the cylinder wall, you can stick that down inside of it with the plungers pushed in and tightened up. And then when you get it in the middle, you release that locking knob and the releases the springs, and the plungers will extend out to the width of the, or to the diameter of the cylinder bore that you're trying to measure. And then you tighten your locking nut back down and it holds them in place. So then you take it out and use an outside measuring tool like the dial calipers then to measure the width of that. So you're basically just transposing a measurement from the telescoping gauges to the dial calipers. So fastening tools, here's the ones we're going to be covering. So wrenches, notice that red text there. You might need to know that later. So wrenches come in standard. If you see SAE, that's Standard for Automotive Engineers, or Society of Automotive Engineers. That is what I refer to as our standard. That's used in the United States and a few other countries. The metric system is taking over, has been for years, and it's slowly taken over most of the world. But still yet, the United States recognizes the SAE as our standard measuring system. So we have sockets that are also available in standard metric. Screwdrivers, pliers, pullers, fasteners, fastener extractors. We'll look more in depth at those. Here's some pictures of the different types of wrenches. So you got boxed in on notice that both ends have a circle on it. So you'll probably have a 1/2 inch on one end and 9/16 on the other. That's typically how those are. Those are 12 point on those. You can also get them in 6 point. The picture on top right, open end wrenches. You've got obviously both ends are open. These are not as good as the boxed end, but they have their purpose. Every wrench is made and have a purpose. If you try to get a lot of torque with an open end wrench, you're likely to strip off the bolt head or the nut, meaning round the corners on the hex head, because it does not grip as well. It only grips on two sides. So, they have their purpose to get in certain places. You have a combination wrench on the bottom right, has your boxed in on one end and the open end on the other. Then your adjustable crescent wrench, notice that's red. Adjustable wrench referred to as a crescent wrench. I think that started with a brand name and then it's kind of stuck with it. And other companies make the same device and it's crescent stuck with it, kind of like channel lock pliers. So we've got Allen wrenches. Those are hexagon wrenches. They're used to take out set screws. There's some cap screws that use hex head. You have a flare wrench there in the middle. It kind of looks like an open end, but you had a boxed end. It's a combination of both. What you use those for is a good example is like a line wrench. I usually call them a line wrench, like a brake line on a car. You've got a flared head that it is on the brake line, and it threads into say, a master cylinder or into your wheel cylinder. If you need to take that nut off, using an open end wrench is not always the best advice on that, because those are most of the time they're on really tight and they're hard to get off. They're corroded on. So using an open end wrench, most of the time will round the heads off, and then you're stuck with using vice grips or something like that, or having to cut it off. So use a flare wrench. It's got that opening on it to allow you to slip it over your brake line, so the metal line will actually go in that slot. Then you can slide the tool down along the brake line to the flare nut, and then you've got looks like 1, 2, 3, 4 sides contacting that nut, so it'll hopefully come off easier. And then you got a striker or a hammer wrench, and that's used instead of using a cheater bar on a regular wrench. And if you don't know what a cheater bar is, that's just as well. But using a striker wrench, they're made to put on a bolt or a nut, and using a hammer on the square end of that. So they're made for an impact, mechanical impact, basically using a hammer on it. So spanner wrenches, these are tools that are used to remove or tighten specially made nuts. You'll see these when we get into our bearing section. We have spanner nuts that tighten bearings up on the shafts, and that's often where you see those. They're different shapes and sizes. You can see the one in the middle in the big pictures, just kind of a curved part with a hook on the end. The hook goes down into the notch of the nut. The pictures on the top right have the hinged, basically the same design. There's just a hinge on them. Bottom right has pins on them. Sometimes instead of having notches in the nut, they'll have a little pin hole or little holes drilled in the sides of it. So you'd use the ones in the bottom right to remove or tighten those nuts. So the socket wrench sets, sockets are pictured there on the right, along with a ratchet that is in the farthest view in the picture, and then you've got an extension. It looks like maybe a 3-inch extension laying there. So the extension goes onto the ratchet, and then you would put the socket onto the end of the extension. If you don't have to use the extension if you don't want to. Basically, the ratchet has a square lug sticking on the other side of it. You can't see it from here, from that angle it's showing, but it's got a square lug that fits into either the extension or the back side of the socket. And those square lugs, you're going to have common sizes. And notice in the red there, they're a 1/4 inch, 3/8, 1/2 inch, and 3/4 inch. They go on and up after that. So we call it drive size. So that square lug on it we refer to as drive size. So you have to have the right drive sockets to go with the right size ratchet. Then you've got different points on your sockets. You've got 6, 8, and 12 points. And one thing to remember, the fewer the points the socket has, the stronger the socket's going to be. So what's pictured there, if you can see that, it's got 12 points on those. So you're not making as much contact on the nut or bolt head as you would with a 6-point. And a 6-point is going to be a thicker wall socket. And we should have pictures of those right here. So the picture down the bottom left shows you a 6-point socket. And you can see the wall thickness is thicker. You've got more contact surface or surface contact with your 6-point socket than you do with your 12-point. So it's going to be stronger. If you got something that's really tight, or if you have impact sockets, they're going to be 6-point. Impact sockets are shown on the right, and those are basically just thicker walled sockets to withstand the force and the abuse of an impact driver. Here's Allen wrenches, the T-handle on the left with a ball end. And that ball end is pretty nice on the Allen wrenches. That allows you to kind of come in at an angle. If you can't get straight on with your Allen wrench, that ball end allows a little bit of misalignment. So basically, the Allen wrench is used for set screws or cap head screws that have the hex inside. So pipe wrenches. Pipe wrenches are used basically for piping and conduit running. There's different angles, different lengths of pipe wrenches. They have serrated teeth in reversed angles, so they grip only in one direction. The head slightly moves. You've got a knob there that turns, and it opens the jaws, it closes them. But the moving jaw, it will kind of flex. It has a little bit of flex in it, it's got movement in it, I should say. So when you tighten it down, that movement along with those serrated edges, reverse serrated edges, they clamp onto that pipe really tight. And they'll actually bite into the metal and leave serrated edges into the metal if you turn hard enough. So you're going to damage your pipe or your conduit using these, but they are a very effective tool um, to tighten or loosen pipe with. But just remember, when you remove your pipe wrench from that, you're going to have some sharp edges on your conduit or your steel pipe. If you want to kind of eliminate the damage to the pipe, you can use what we call a strap wrench or a chain wrench. Chain wrench doesn't do as much damage to the pipe as a pipe wrench would do. So what that does is you wrap the chain around your piece of metal, around your pipe or your conduit, and you've got a catch that you lay your chain into, and then you just rotate it, and the chain tightens up around it. And then it tightens only in one direction. If you need to go the other direction, you remove it and flip it around. Same with the strap wrench. You have the strap that goes around your pipe or your conduit, tightens up as you rotate it, and it grips onto the pipe and tightens it up, and it doesn't damage. So torque wrenches, these devices are used to tighten to a certain rotational torque. Torque is always in a rotational manner. So you've got different versions of these torque wrenches. The one on the left, kind of the middle of the slide, is a clicker type. That is probably the most common today. We've got a micro, like a micrometer adjustment on the end, and each manufacturer has a little bit different ways of locking that. So I know like Proto and Snap-on, things like that, around the right in front of your hand, there's a collar or sleeve that you've got to pull back, and then it'll rotate. And when you release that, it springs back and it locks it in place, and you can't accidentally change it then. So what you do is turn the micrometer to your setting. Say that particular micrometer may read from 25 foot-pounds up to 250 foot-pounds. So you set your setting somewhere along that range that you want to tighten your bolts down to, say 110 foot-pounds. You set the micrometer reading on 110 foot-pounds. Then as you start tightening it, when you get to 110 foot-pounds, you need to be moving really slow with it, because you can't over tighten it using these. So as you creep up on that and get tighter and tighter, it'll click, it'll pop. The higher the torque, the more audible and more you actually feel it in through the handle of the torque wrench. If you have lower foot-pounds, you may not hear it or feel it as much, but I mean, it will be audible and noticeable. But I've got a torque wrench checker at work that we calibrate torque wrenches with, and it goes up to 2,000 foot-pounds. And I can tell you, when you start cranking down on a 2,000 foot-pound torque wrench, it's about 12 feet long, and it's bowing about 4 inches in the middle. You kind of cringe when that thing gets up, around 1,400 foot-pounds and on up to 2,000. When it pops, you know it. It's really loud. Anyway, moving on. The middle one is not as common. It's a dial type torque wrench. You just read your measurement from the dial, and there's really no setting on it. You just, as you tighten it up, the dial turns, and you watch where you want to stop it at. So if you want to stop 110, you watch your dial. The beam type on the right side, that's probably, in my experience of calibrating torque wrenches and using torque wrenches, that's probably the one I can take out of my toolbox and feel most confident that it will be accurate. Because the clicker type, the one has a micrometer adjustments, those can, if you leave it tightened down, say if I left it on that 110 foot-pounds and threw it back in my toolbox and not use it for 6 months, I've left that spring basically charged, pressed down. for that long, and it's going to be out of tolerance. So if I try to use it again, the 110 foot-pounds may be more like, 105 foot-pounds, and I wouldn't know it, or 100 foot-pounds. It's going to be off some, and it matters when you get into certain things. You build engines, things you really need to have pretty close. But on the beam type, it doesn't do that. As long as you take care of it, they stay pretty well in line, and they're not as easy as a reed. You get a little bit more error margin for error in that. But here's how a beam type works. There on the top, you see you got the scale. You've got actually two rods. You've got the beam, and then you've got the pointer arm. So as you start to gain torque on a nut or a bolt, actually the beam, the bigger bar starts bending with it, and then the pointer bar stays straight, and then it shows up on the pointer on the scale of how many foot-pounds you've achieved with that. So that one you can see in the second picture is 25 foot-pounds. So the bottom one just shows your clicker style. That's another one's just kind of got a different type of adjustment on it than a micrometer. So here's screwdrivers. I'm assuming everyone may have seen or used screwdrivers in the past. So we've got the three different parts: tip, shank, and handle. The tips come in different shapes and sizes. We'll look at those in a few minutes in some other slides, but some safety things with screwdrivers. Don't use them as pry bars, not that anyone would. Don't use them as a chisel, not that anyone would. And then another tip I like to tell students and people listening, probably, if you've been around screwdrivers and use them, you've probably done this very same thing. So you're right-handed, which I am, and use a screwdriver with my right hand, but I'm holding the part in my left hand, and a screwdriver slips and jab the tip of that screwdriver down half inch down into the palm of your hand. That hurts pretty bad. So that's just a tip of, if you're using a screwdriver, be careful of that tip slipping off and jabbing into your hand or your arm or however you're using it. So there's some tips your screwdrivers can come with, and the type of screw, what the screw looks like to made up with it. So there's safety tips. Kind of already mentioned some of them, but one thing I'll point out is the third bullet down: never expose a screwdriver to excessive heat or cold. I won't say that for every tool, not just screwdrivers, because tools are made with hardened steel, and when you heat things up, they lose their temper. And so if you heat something up like welding, if you have around welding or have it in a high temperature location, then you can distress the metal and weaken it. So don't ever get them around heat or too cold. I'm never really had a case where I got one that's too cold, but I guess it is possible. A liquid nitrogen or something, but who would have that laying around? Let's see. Trying to look to see if there's anything to mention about this. The bottom one there, talking about vinyl covered blades. These you can get electrically rated tools that have a vinyl covered shank on them down to the tip. So those are used for electrical purposes, for energized electrical tools. So we're going to look at pliers now. Actually, it used to go through all of those pliers, and I've kind of cut it down to less than half of those now. So slip joint pliers, these are your typical household pliers. You've got two adjustments on those, typically two adjustments. Maybe you might find some that's got just one or maybe three adjustments, but just common household pliers. They're adjustable, 6-8 inch, maybe smaller or larger. They don't grip really well. They're not the best tool to grip with, but they have their purpose, as any tool does. Getting in the channel locks, these are tongue groove pliers, I should call them. This is what we refer to as channel locks. Notice that's red. These are really good gripping tools and or pliers. This particular one has a different shaped head on it. Notice the jaws on them are V-shaped, and that's more for gripping pipe. Your most common channel lock pliers are going to have a flat surface with serrated teeth, and they'll be used to. So the most common is going to have your flat jaw channel locks. These come in different lengths and different sizes. You can get them really small, pocket size, up to probably some open. The jaws open up to maybe 6 inches or so. Maybe larger. Locking pliers. These are known as vice grips, vice grip pliers. They clamp down like a vice. They firmly grip objects. Look down at the picture. You can see that how the handle opens up. You've got a little lever sticking out there. You press that lever and it opens it up if they're locked down. Use a regular handle part there to open it up, and use your knob to adjust opening of the jaws. So if you have an object that maybe is 1 inch in diameter that you want to grip, you need to loosen that knob in the counterclockwise direction, and it's going to open your jaws to about a 1 inch opening, and then you can clamp down on the 1 inch object, and you want to have just a little bit of pressure on it to where as you squeeze it, it'll pop closed and hold itself there, and it'll actually lock onto it. So these good pliers, they have their purpose. If it's something you can't grip with, say a channel lock plier or something like that, these are really good to clamp down on, to try to loosen something, or just to hold it to while you're trying to use a screwdriver to take screws out of it or something. Needle nose pliers. These come in different shapes, sizes, curvatures. These are basically to get into tight places to where normal pliers can't go, or they're used to handle smaller objects like snap rings and things. So things that's maybe too small to handle with your fingers, you can use needle nose pliers to handle. You can get some that's got the long jaws, the curved tips. They all have their place, their purpose. Some have cutting edge built into them, like the picture on the right. You notice down at the bottom of those jaws, it looks kind of dark gray there. That's a little cutting edge when you can cut some wire. So here's lineman's pliers. These are really thick, heavy-duty pliers. If you turn them sideways and look, they're about 3/4 of an inch wide. They're pretty heavy-duty. Have a good solid cutting edge there in the middle part. Good gripping jaws, insulated handles. But this particular one is not rated for electrical hazards. The ones that are have really thick orange type handles. But these are a good common plier. They're not the best gripping type plier, but they're really good for twisting wire. That's what I use those quite often for. In cutting pliers, these are used to cut close to the workpiece. Notice that red there. We've got diagonal pliers, and these just all they do have a cutting surface, used to cut wire only. Pullers. So we've got 3-jaw and 2-jaw pullers shown in the pictures. There's really no difference in them. The 3-jaw is just going to put the pressure or the load in 3 points across a gear or whatever you're trying to pull, as opposed to 2 points. So you can see the picture on the right. It's mounted up on a gear, the 2-jaw puller. The threaded rod it's going through the body of the puller is threaded inside of that the top body of that, and it's pressing against the shaft that the gear is mounted on. So as you tighten the hex end on the top of the threaded rod, all the way to the right of the picture, as you tighten that down in a clockwise fashion, that's going to draw that body of the puller toward the hexed part, and it's pushing the threaded rod's pushing against the shaft. And as the body moves, it pulls the jaws with it, and it's going to pull the gear off the shaft. So that's how that works. And so the 3-jaw, only thing it does is just, it's better to use the 3-jaw when you have it and you can, so it can spread the torque out across, or the pressure out across 3 points of the 2. So here's some shows 3 different common types of vices. Notice that's red. You'll need to know the different types of vices. So top left, you got the utility bench vise. That's what we have in the lab. Actually, we have all of these in the lab, sorry. But the bench vise is mounted on all their benches throughout the lab. The machinist vise, you'll find these on the drill presses. And then the pipe or yoke vise, you'll find that somewhere in our lab. It's on a rolling table, so it's hard to tell where it's at any given time. Cutting tools, we got hacksaw, different frame sizes of those. Different manufacturers kind of make them a little bit different, but they're all essentially the same blade. Your blades can come in different numbers of teeth. You get them for like 32 teeth per inch, or measure TPI, teeth per inch, or down to like 12 teeth per inch for cutting like wood, and 32 teeth per inch be cutting thin metal with it. So you got the mini hacksaw. It's usually the same blade. You get in some tighter spots with those. Hacksaws only cut in one direction, so you need to have the teeth basically pointed away from the handle. So when you push the handle forward, it bites in. When you draw back, it's not cutting, so you relieve the tension off the blade when you pull back. So here's what a cross section looks like of the hacksaw blade. Got the raker tooth, wave tooth, and straight tooth. Picture down the bottom shows your 14, 18, 24, and 32 teeth, and what they would applications they'd be used for. So basically, the rule of thumb with that is thinner the metal, the more teeth per inch that you need. So the thicker, I wouldn't say just metal, you can use it to cut wood as well, but that's what it's showing as a piece of pipe. So if you cut thin wall tubing, you want a 32 teeth per inch. So you can have more teeth that's in contact with that with the thin metal. So if you have thicker metal, then you can use a larger teeth per inch. So using a hacksaw, they cut in one direction. It's what they show the directions here is secure it in the vise. You mark where you want it to cut at. You use a file to start a little notch in it, and then that way the notch kind of helps the blade to start. So notice the word files is red. So you need to know the different types of files, and you got the front view and then a cross-section view of what the files look like. So the flat, mill, 3 square, round, square, half round, and knife edge files. So these have serrated edges on them, and they're used to, the ones that's shown here, you can use to do metal and wood. There are some that's made just for wood that you don't want to hit on metal, and those really have thicker serrated edges and referred to more as rasp. Or then these files are, you can get them coarse and fine as well. So here's showing some different cross sections, how they're manufactured. You've got the flat and rough, second cut, and smooth. So in the rough cut. One important thing that about files is when you buy new ones, they're really sharp. This says to kind of knock off that sharp edge by filing brass, to kind of break them in. I've never done that, but one thing I have been taught years ago by a mechanic is when you're storing your files, don't store them in a manner that they're going to hit each other, particularly if you're transporting them, like in a tool bag or something. If they hit each other or other hardened tools, you're dulling your files. So try to take care of those and keep them in a pocket by themselves to where they don't bounce and hit against other hardened tools to dull them. So using a file, this is showing the direction, kind of like hacksaws. These are used to cut in one direction. on the forward stroke and you pick it up on the reverse stroke. Taps, we have to talk about taps and dies. Taps are used to cut internal threads. Basically, you've got you drill a hole to a particular size, whatever size tap you're using, and then you got the taper tap to start it with. You got a plug tap and then a bottom tap. Use a bottom tap. You want to, if you got a blind hole, say you've got a 4-inch thick piece of metal, but you only want to tap a hole halfway down through it. So you're going to tap it 2 inches down, and you want the threads to go all the way to the bottom. So you start out with the taper tap, but you notice the tip of that tap is it doesn't have threads all the way to the end, so that helps you get it started. But then you go to the plug tap, and you got a slight taper on it, and then once you tap all the way to the bottom with the taper or plug tap, then you use the bottom tap to finish your threads all the way to the very bottom of that 2-inch hole. Otherwise, if you don't do that, you'll only have threads about 3/4 of the way down, or at least your bottom ½ inch probably won't be fully threaded of the hole. Get the adjustable handle, tap handle wrench there shown at the bottom. These are dies. These are used to cut external threads. So if you have a piece of rod stock, you can actually cut threads on that and make a bolt out of it, or a threaded rod. So using the thread tap, so when you use taps, you want to use good lubrication. You want to, I can't stress that enough about using a thin oil. They actually make cutting fluid, tapping fluid for that. But if you can't find anything else, use a thin oil somewhere around the vegetable oil weight. It would be fine. If you have nothing else, use kerosene. But you need some type of lubrication on that. I've used WD-40 when I didn't have anything else, though WD is not a lubricant per se, but it does help ease up the friction somewhat. So using a tap, you want to drill a hole to a certain size, and we have charts, and we'll go into more detail on that later. But then when you start your tap into your hole to make your internal threads, you want to turn about a 3/4 to a full turn in a clockwise direction, and then you want to back it off about a 1/4 of a turn. And when you do that, you're breaking the chips. When I say chips, if you've ever drilled a hole with a drill bit, and you have the shavings come out, and maybe a long spiral shaving, well, the taps are making that shaving as well. But you don't want that in a tap. You want to break that off in small little pieces and have those little pieces come out the flues of the tap, those little grooves on the side. So as you're tapping, you go about a full turn, and then you back it off a 1/4 turn. You actually feel that you can feel it break the chip up, and then it makes a little small piece, and as you tap it, it'll start working its way up through the flues. So here's some tap magic. Always use cutting fluid or some type of fluid on it. That protects your tap, makes it good threads as well. Bolt extractors, if you're unlucky enough to break a bolt off into a piece, they are devices that are particularly made to get your broken bolt out of a hole. You got different shapes, sizes. The fluted type on the left, square tapered on the bottom right. Those particular two, what you do is drill a hole to a certain size into the broken off piece. So you try to get us to the center of the broken bolt as possible. Drill a hole, and then the fluted type and square taper type, you drive those in with a hammer, and you actually just friction force to drive them in, and then you use a particular wrench, whatever fits at top, a crescent wrench, to turn it in a counterclockwise direction if it's a right-handed thread bolt. The ones in the top right, those are spiral type. You actually drill them to a certain size hole. Those are left-handed threads onto the extractor, and as that starts to tighten into the broken section of your bolt, it actually tightens in a counterclockwise fashion, which is going to loosen up your bolt that you broke off, assuming it's a right-handed thread. Which most things are right-handed threads, or applications where there's not. We'll talk about that in a different section. So the drill out type bolt extractors. I've never used those personally, but they look very interesting. Look like a pretty cool tool. They actually drill a hole and thread themselves in and remove the bolt all in one tool. So that looks pretty neat. So here's kind of some pictures of using the extractor. So you drill a hole down the center of the center as possible of the broken bolt. Make it to the right size of your extractor. That particular one shown on the bottom left, it's kind of it's a wedge type. You put it in, and then you back it out with a wrench. Pretty simple looking to pictures there. So tin snips. These are used to cut tin, obviously, thin metal, thin sheet metal. You can use it to cut anything thin, per se, like mesh wire, leather, and it says asphalt roof shingles, but I've never used them to cut roof shingles before, but maybe roofers do. I don't know. They're not ordinary scissors. They handle pretty heavy duty cutting, although it's, anything over a 1/16 of an inch, I would say is going to get pretty hard to cut with tin snips. Now they have three different configurations, three different shapes of the teeth. And if I remember my color coding correct, the one on the left, the red ones are used to cut to the right. I've always remembered red right. So if you want to say cut a circle out and you're going to cut it in the right hand fashion, you'd use that. If you're going to cut it in the left direction, then you'd use the green ones. And if you want to cut a straight line, you would use the yellow ones. So they'll be cutting straight. So you want to just cut a piece of metal in half, right down the middle, or a section of it off. Use the yellow ones. All right, looking at some hammers. So we've got a claw hammer. It's your typical carpentry hammer to drive in nails, and the claw part is to remove nails. If you can get the nail head started into the claw part, and you pull back and have mechanical advantage to remove the nail from the object you're trying to pull it from. You don't want to use a claw hammer if you're using it as a carpentry tool. You don't want to hit on any other type of metal. I've talked to carpenters, and they can tell when somebody's used their hammer on beating a piece of metal or concrete. So you wouldn't use it like you would a ball peen hammer. And speaking of ball peen hammer, this is used for shaping and straightening unhardened metal. So this is what you'd use for driving in those bolt extractors, using on chisels, things like that. So this is your metal type hammer, and you wouldn't particularly use this for carpentry either, because the face is not designed for that, but you can drive a nail with it, particularly the hardened concrete nails. You probably certainly use it for those. Dead blow hammers. These are basically, when you say dead blow, it's when you hit them against something and they don't reflect back. They don't bounce back. That one picture in the top right, use those quite a bit where I work out, and if you shake them, you can actually hear some kind of media inside of it. I don't know if it's sand or lead shot or something, but it's what it sounds like when you shake it. And if you think about the momentum, the motion of that, if you take that hammer up in the air and you're going to slam it down on the table or on some surface, as you take your force downward, that shot or lead or whatever's inside of that would fly to the top part of that. Okay, and then when your face strikes the surface, your face hits, and then all of a sudden that sand or shot comes in behind that and hits the back side of that, inside of your hammer, and it keeps it from bouncing back up. So it's a dead blow. That's what it means. And then the other ones there have interchangeable faces for different types of softness of rubber. So this is a popular hammer used by machinists because they don't mar the work surface. They don't dent it. They don't leave dent marks and wave marks and things. So Here's some different types of punches. We'll go through all of those. You can see the pictures and they're kind of self-explanatory. Your center punch really is what you're going to be using in the lab. When we start drilling, you'll center punch holes in or center punch, metal to start a drill bit with. So cold chisels, these are used to cut steel with, cut metal. They're different sizes, different shapes. Kind of self-explanatory with that. One safety rule I always try to mention about these. Notice the pictures on the left. That's what they're supposed to look like, and the picture there in the middle, they should not look like that. So the picture there in the middle, they should not look like that with the mushroomed head. That occurs after repetitive hitting, beating, and it kind of flattens out the metal, makes it roll over. That mushroomed head can become a danger if it's hit or struck in the certain, if you say the right or the wrong angle, and those pieces can chip off and fly. I've heard that they can fly at the velocity of a .22 bullet. I've not seen that per se, but I can see where that could easily happen if you hit it in the wrong angle and break a chip off of that. So if your chisel starts looking like that, take it to the grinder and grind that mushroom head off of it. So levels are tools used to determine both how level and horizontal a surface is and how plumb a vertical surface is. They have different lengths, different shapes, different sizes. They typically have a glass tube with some type of material in it. Ethyl alcohol is common, depending on the manufacturer and where it was made and what it's made for. Not a whole lot to talk about a level. You got a bubble in it. You line up the bubble with little black marks and determine if it's level. One thing you keep in mind though is your bubble always goes to the high side. So we got a camper and we try to level that up by the level I've got on the side, and I always tell my wife, I said the bubble's to the high side, so she can look at that and tell me which way I need to change the position. So anyway, bubble goes to the high side on a level. All right, a plumb bob. This is a heavy weight or a weighted object that points down. So typically a string's gonna go to the end in the top of that, and it'll hang down straight. So an example I usually use in the classroom is if I want to mark a spot in the floor directly underneath the sprinkler head, I could take that string that's tied to that and tie it to the sprinkler head, and that gravity is going to pull that weighted object straight down to the floor, straight beneath that sprinkler head, and that pointed tip is going to point right directly underneath the sprinkler head. So that's where I can make a mark, and then if I can want to dig out a drain or something, that's where it's going to be at. That's about the best example I can give for a plumb bob. All right, we're getting into the end of it now, the hand tool safety. Shooting for 1 hour and about to overgo that. But hand tool safety. The number one cause for accidents is carelessness. Only use tools for their intended purpose. Safety glasses are your most commonly used PPE. And those three are red. You can read down through the other ones. If you're on leisure, we've got the presentation available for you. So best practice, best maintenance practices is the best type of maintenance is preventative maintenance. And that is opposed to reactive maintenance, which is repair it when it tires up. Or preventative maintenance is try to do steps along the way to prevent it from tearing up, like change your oil in your car. That's preventative versus letting your car run until the oil's nothing left, no viscosity left in it at all, and then it crashes your engine. Or There's another type of maintenance called predictive maintenance, and it's not practical in most applications, but you talk about oil, you can send oil samples off to have it tested to see how much viscosity is left in your oil. So, for car maintenance, it's not worth that. But when you get into industrial machinery where you have thousands of gallons of really high dollar expensive oil, it's worth to have a program that has predictive maintenance. But, you know, the best overall type of maintenance is preventative maintenance. And you set it up on a frequency that's recommended or studied. It's best to troubleshoot in stages. And the education, training, and I highlight good attitude, make a more valuable maintenance technician. I would rather have someone coming in my crew um, that has a good attitude than all the education and training in the world. I can teach someone that has a good attitude, but someone's got a bad attitude with all the education and training, I can't teach them. So um, when I hire somebody in my crew or whatever, I try to look for a good attitude. So I highly recommend that to everyone all the time. Keep a good attitude for what you do, and you'll be a more valuable asset to the company that you work for. So safety, uh, your fingers are also a tool, and you want to take care of those. So the wedding ring is one of the most dangerous things you can have on your hand. And you can see by the pictures what rings have done to people's hands. You can look it up on Google if you dare do it. The ring deglove, where rings get pulled off and it takes the finger with it. It's pretty gruesome. I don't recommend it, but if you want to do that, that's up to you. But they make silicone rings, and instead of the gold or titanium or whatever type metal ring that traditional. I wear a silicone ring all the time. You can get them pretty cheap. That way they're designed to break like 40, 45 pounds of force, and that's well below the threshold to pulling your finger off. And never use the top left picture is using a cheater bar. So wrenches are only designed for so much torque. You put an extension onto that, you're going to gain a mechanical advantage to get more torque at the bolt or nut head, but you're also taking a chance of breaking the wrench and hurting yourself. So that's some do's and don'ts there. And some more do's and don'ts. Don't use the screwdriver as a chisel. All right, got any questions? Feel free to email d2l or northeast8.com or call me if you need to, and we'll just follow up with questions on our next Zoom meeting.